Okay, so we were talking about here about the idea of projections. So now, as we said, R prime can be written as Fs plus Fn, and at the same time, it can be written as the summation of Fc plus Ft. Okay, so now if I decompose, so this is Ft, okay, and this is Ft. If I decompose Fc and Ft on shear direction and normal direction, I should obtain that the projection on shear direction should give me Fs, and the projection on normal direction should give me Fn. So if I look at my figure, I have that Fc is doing with Fs an angle of phi. So the projection on Fs will be Fc cosine of phi, and it's a positive projection. While for Ft, as you can see here, the projection will be negative. This is why it is minus Ft sine phi. And now on the normal direction, if I project both on Fn, both will have positive component, as you can see here. So it's plus, but now concerning the angle, since the projection on shear was Fc cosine phi, that on n, I take the angle which is pi over 2 minus phi, so it's or cosine pi over 2 minus phi, or it is sine phi. So plus Fc sine phi and plus Ft cosine. Now, once I put these relations, okay, by proper, if you want, just solution, I can find the expression of the cutting force and the thrust force. I will find them function of the shear force and the angles uh, beta, alpha, and phi, where we have that alpha and phi correspond to alpha the rake angle, phi the shear angle, and beta is given by the friction coefficient. Okay, and Fs is the shear force in the plane of shear. So in this way, I can calculate the value of uh, cutting force and thrust force. And Fs can be calculated by the shear strength S, okay, times the area. And we know that the area is T0 omega over sine phi. So to calculate the shear force, we can replace it by the shear strength times the area. Okay. So this is how I can calculate the cutting force and the thrust force. Any question until here? Okay. So now, by proper arrangement and use of the previous equations, we can demonstrate, okay, the following relation. We can say that the value of shear stress can be written as the shear stress in the shear plane can be derived function of the cutting force and the thrust force as Fc cosine phi minus Ft sine phi over the area. Okay, and all we did is here we can just replace the shear force we got from this formula here. So here we calculated the shear force, okay? The shear force can be calculated function of the cutting force and the thrust force, okay? So we can just replace the value of Fs in the expression of shear stress. So this will give me a relation between, that is Fs over A. This will give me a relation between the shear stress and the cutting and thrust force. So in the problem, it depends on your input. What are the forces you know? And you can deduce all other forces. Okay. Now, um, a science, we have that a scientist called Mershon did some experiments, okay, and he reasoned that all of the possible angles emanating from the cutting edge of the tool at which shear deformation could occur, we can find just one angle that will be optimal. Okay, so he tried to see what will be the optimal value of shear angle for a best cutting operation. So this angle at which shear stress is just equal to the shear strength of the work material, and so shear deformation will occur at this angle. So what he did is that he found the expression of shear and he derived this expression to get the value of minimum. Okay, so he said that in fact the work material will select a shear plane angle that will minimizes energy. This angle can be determined by taking the derivative of the shear stress in the equation with respect to phi and setting the derivative to 0. So after finding the expression of shear function of phi, he said that to have an optimal cutting operation, I should minimize energy while obtaining same performance. So I should find for a certain cutting operation, what will be the minimal shear that is possible will correspond to which angle. So when he derived this relation, he come up with the following relation for phi as function of the rake angle and the angle related to friction. So the optimal angle in his derivation was phi equals to 45 plus alpha over 2 minus beta over 2. So if they ask you what is the optimal cutting shear angle, you can use this formula. And also, if you are interested in complete derivation, all of these derivations are in the YouTube links I posted for you. Okay. Now, concerning the analogy, we have seen it together. So after developing this model, this development is for the orthogonal model. Now you can extend all relations calculated. You can extend them to the turning operation. Okay. So for example, the removal rate is, let's say, is calculated as, how we calculate the removal rate here in the orthogonal model. In the orthogonal model, the removal rate is equal to T0 times W, okay, times the velocity. So here, by analogy, in the turning operation, we replace T0 by the feed, we replace W by the depth, and for the velocity, it's V. So in the turning operation, for example, the removal rate can be calculated as the feed times the depth times of the cut times the velocity, the turning velocity. Okay? So, and of course, all forces, all the derivation of forces relations can also be applied in case of. Now, in the last step, we will define power and energy relationship in machining. So, since time is over, we will continue this part next time and we start to do problems. Okay? Any question before we start? Okay, guys, thank you. See you next time. Bye bye.
Thank you, doctor. Bye.
Doctor?
Yes?